Cool. Hey, everybody. This has been really amazingly awesome so far, and it's just, like Matthias, I'm pretty nervous because there's just so many smart people in the audience, and I'm sure I'm going to get trolled, so I'm just preparing for that. Emotionally, I have been for the past couple weeks, so that's okay. So today I'm going to talk about correlation. We've heard a lot today about kind of, well, Jason sent us an email a couple months ago when everyone who was going to speak today about, like, it was really inspirational, but also like a big order to fill, basically, of like, hey, I don't want you to just talk about tools. You got to talk about what the future is. And I think everyone was like, So I have no idea what the future is, but I'm really excited to talk about a challenging subject, which is correlation. And I don't proclaim to be an expert on it, but I have a bunch of ideas, so I'm going to get into that. So like Jason said, I'm the CTO at Paperless Post. CTO actually stands for Chief Taco Officer, not Chief Technology Officer. It's really important that that distinction is made. I have been a developer forever. I'm recently more of an ops person, and recent because as Paperless Post as a company scales, but I'll talk a little bit more about that in a second. But just as a background, like, I'm not a business guy. I care about my business doing well, but I am a programmer at heart, and that's basically what I do 24/7. Really quickly, Paperless Post makes pretty things. That's what we do. A bunch of you probably received one of these at some point, but basically we send online and offline stationary invitations, and making pretty things is what we do, so we want to do that on our back end and monitoring too. Basically, paper's going to pay. So a little bit about me, and this is what I was going to get into, just as to frame this conversation. Something I'm an expert at is eating. That's what I'm really good at. So this is going in order of how good I am at things. I'm really good at eating, which means I eventually got pretty good at cooking because I couldn't eat shitty food, so I had to get good at cooking. In terms of experience, I have a lot of experience in Ruby and JavaScript. Actually, 4 years ago, almost to this day, like, I stood at this podium and gave a talk at the first jQuery conference in this place. And at that point, I was doing a lot more JavaScript, and so now I'm at an ops conference. I don't know how that happened. I'm a growing student of operations, I would say. So experience in Ruby and JavaScript, I'm learning operations, and the way I'm doing that is I manage somehow to hire 4 really, really brilliant ops engineers, 3 of which are here today, and you should definitely say hi to them, Johnny, Bethany, and Alex, who are awesome. So definitely go say hi to them. And they're all 3 of them, and our 4th, Mr. Dan Diego. His name's actually Dan Condamiti, but he lives in San Diego, so we call him Dan Diego. I actually only recently learned his last name. I'm a really good manager, as you can tell. We are kind of distributed. We have one guy, Alex, in Massachusetts, and but the rest of the company is in New York. I was living in California for 2 years, and then just moved back to New York. And then finally, really, really early days, and I think as a whole, our community, we've done distributed systems for a while, but I think we're all really trying to figure out how to do that at scale. So first of all, I just want everyone, so I showed these slides to the rest of my team, and no one knew what DAP was. Does everyone know what DAP is? So DAP is like, when you give each other DAP, no, it's actually not this, it's boom, boom, boom. That's DAP. So everyone, turn to the person next to you and give each other DAP. Just do it, please, for me. Okay. It's like a high five and then the pound. Okay, awesome. I'm sure that was really fun. Cool. So, give each other DAP because we have data now. Yeah. Before we didn't have data, and we like a year ago or 2 years ago, when I think everyone was talking about monitoring and talking about ops, a lot of it was just like we didn't know what was going on. We didn't have 1 second resolution. We didn't have 10-second resolution. We had every night, Munin or whatever graph that just sat on a server and wasn't real time, and that was data. And now we have a lot of data. Epic was supposed to use Graphite really heavily, and we wrote our own little dashboard. And so we have like so much data in Graphite. We have data in logs and Logstash. We just have tons and tons of data. So that means we were like, oh yeah, we need to solve the data problem, and we did it. We did it. We solved the data problem. So no more tears, right? What? No, actually, we did not solve anything. Well, we solved something. We solved that we knew we had more problems now than we ever did before, which is something. So we should still be proud of that. But now we're moving on to the next phase. So in my mind, Cliff talked about this before, and I think there's a lot of overlaps between all the speakers today, which is really cool, which means maybe I won't get trolled as hard as I thought I would, because maybe everyone agrees kind of on some basic facts. So in my mind, the levels of monitoring Nirvana are, it's like a hierarchy of needs, a triangle. Anyone who's read Maslow, hierarchy of needs, it's like a triangle with the top is being really perfect and the bottom being like generally what everyone needs on the basic level, kind of like a food pyramid, but not exactly. So at the bottom is pure data, right? So now we have this. We have pure data, which is just an insane amount of just numbers, information, events, whatever it is. Above that, which is kind of what I want to talk about today, is we have basic inferences and correlations. So from that data, we've extracted some kind of meaning that these two data points are related to each other, or these two systems of data are related to each other, and we can draw conclusions based on that about what our systems are doing. And then at the top is the fucking matrix. So I should have just put OSPA in there, but I didn't. So what I actually mean is pure data, basic inferences, and correlations. Then eventually at the top, the dream, like this serious dream, is to have these predictive and direct relationships between disparate pieces of data. So if you have all this data, imagine a world where the data itself knows about other pieces of data and can make conclusions about, I'm not even talking about auto-scaling, I'm not talking about, auto-acking or anything. I'm really talking about, actually being able to know when to scale up, to know when your system is not just kind of fucked, but really fucked, and the differences between those from your data and not from a human being, or somewhere in between. So that second level, what does that mean? So correlation is really just about aligning the data. So I was really, really interested in what that meant, or what I knew about correlation. We joke that Johnny, our director of ops, is the master of correlation. He's kind of has like a wizard sense of like, he can just look at a set of graphs and be like, these two things. And that's awesome, but not everyone has that skill. So I started reading about statistics and started reading about, ops, as a bunch of people in here have already said, and monitoring isn't something that just web companies do. It's something that's been around for a long time, and statistics obviously have been around for a long time. So when I started reading about it, the first phrase that kept coming up was, yeah, correlation is great, but correlation does not imply causation, meaning that you can know that these two pieces of data are related, or they seem to trend together, but that doesn't mean that one affects the other. And the classic example of everyone gives about correlation, you can't really read the bottom, but that says the marshmallow test. How many people have seen this video, have heard about the marshmallow test? So it's a classic psychological example, basically, where they gave children a marshmallow. They sat them in a bare room and said that if you can sit here and wait and not eat this marshmallow, in 15 minutes we'll give you a second marshmallow and you can eat both of them. And it was a study of child behavior and being able to wait, and basically a lot of kids ate the marshmallows. Come on, how are you not going to eat the marshmallow? But the kids who found out how to distract themselves and could wait, actually got 2 marshmallows, and they were really happy. But the original study was happened in the 60s at Stanford, and they followed these kids throughout their life, and later in life found that the kids who were able to wait, there was a correlation between the kids who were able to wait and people who later in life lead more successful lives. Isn't that crazy? So, they took a pretty big sample, but they thought that if you could basically just wait in this very simple test to eat a marshmallow, that 15 years later you were a successful person. If you couldn't, some of the people were in jail, some of the people were like just were on meth, you know, it was just like really bad, just from eating this marshmallow. So obviously those aren't actually necessarily perfectly related, but there is a correlation, meaning that these two things might have influenced one another, and obviously there are a million of other variables that could be out there that could have affected that. But what correlation can do without actually, implying full causation, it can let us narrow our work. So we were talking a lot about today about being happy as an ops engineer and just being able to take time off. And for me, taking time off is about shaving yaks and like building cool stuff that we might not need. So if we can correlate and narrow our work so we don't have to spend so much time thinking about all the data we have, then maybe we can get back to doing the things that are more fun. So there are a couple types of correlation that I want to talk about today, and then talk about kind of like how maybe we can put these together. So this is the hardest one for me. I'm marginally better at math than I am at spelling, and I'm really bad at spelling. So watch out. But I've been doing a lot of reading, so that counts for something, I hope. So the first thing that every statistics textbook talks about when they talk about correlation is this Pearson product moment correlation coefficient. I can't even say it one time as fast. But basically, it's a way of taking two axes or two sets of possibly disparate data and kind of judging if they're correlated using math. So here's a simple ops-related one. Obviously, these are fake numbers and a fake graph. But like, let's say, when your CPU on your web app server goes up, you pretty much think that your average response time is also going to go up. So you plot the numbers on the graph, and you can this is obviously a bullshit graph, but you can pretty much see that these two are correlated, and you could draw a line across the middle and see that these numbers kind of follow this line, so that in a direct relationship, when CPU goes up, response time goes up too. And these are things that we care about as ops engineers. So here's the Pearson product moment coefficient. It's not fraternity. Don't get it confused. That's what I thought when I first looked at it. It looks really complicated, but it's actually really, really easy to calculate. This is in Ruby, which is my second native language. So all we're doing, the basic math of it is you're just taking standard deviations of all the numbers in that, or you're taking the standard deviation of each axis, of each set of data, and then you're subtracting the individual data points from the standard deviation and the mean, and then seeing the distance the average distance away from that kind of straight line, and then summing them up and averaging the whole thing, and you get a number that's somewhere in between -1 and 1, basically. So I'll post these slides so you can look at this more, but it's really, really, really straightforward. But basically you get this number that at the bottom it says 0.9265. So these numbers are really, really correlated. The general idea is that the closer it is to 1, or absolute 1, the more correlated these numbers are. And this is pretty cool. It's pretty cool to know that just from looking at a large collection of data, we can actually know generally if the numbers or the points in that graph are related to each other. So in general, here's what Pearson does. It gives you close to absolute 1 equals probably correlated samples. Obviously, this is statistics, so everything is like, maybe. There's no absolute truths. But some interesting things about it is, like, could we apply this function, which we definitely could, to moving averages and to graphs that we see every day? Could we pack it into Graphite? Maybe. I think we could. Maybe we can do that tomorrow. Obviously, there's some limits of mathematical correlation. One, it kind of requires known inputs. So I put CPU and response time because I assumed or thought that they were correlated. But you have to know kind of what you're putting on your X and Y axes and guess that they're correlated first. In theory, you could put every metric that you had in Graphite and somehow see if each individual one was correlated to another one, and maybe that would take like 3 years. But you would eventually get data out and maybe be able to rank them in terms of correlated numbers. like I said, statistics is like, maybe. So there's a suggestion of correlation, not proof. You can't actually prove that these two numbers are correlated. Or you can prove that individual numbers are correlated, but not the collection of numbers. And you kind of need a large amount of knowledge of the data set to make any decisions based on it. Like I said, if you need known inputs, you kind of need to know that what you're putting into these functions. So the second one is, which we're much more familiar with, I think, is time-based visual correlation, and this is something that Boundary and a lot of other tools are really good at. So I'm going to tell a graphite story. This is an actual graph. I couldn't find the big one, but this is a snip from our campfire room. So it was November of last year, and every 30 minutes or so, we thought it was around 30 minutes. We couldn't really tell. Like, our load balancer would just start dropping traffic, or it would just like dip, and we'd be like, why are the number of requests dipping every 30 minutes or around 30 minutes? And we thought about it for a little while, and like, it must be a cron job. So we looked at all our cron jobs. That's usually the case. It wasn't a cron job, and we couldn't figure it out. We thought it was our web app server. Something about our web app servers were dropping. Eventually, we tracked it down and saw that actually on the load balancer level, on the HA proxy level, we were seeing these same dips in traffic. We were just serving less requests. It can't be any way that people just only hit the site in between these 30-minute marks. So what could it be? So eventually, we started to look at other graphs. What was taking a bunch of time on our load balancer server? We saw that CPU time and load average went up at around the same time. And this is kind of like a bad version of that graph, but requests went down, CPU went up, and we could visually see that. So then we just started like, okay, and we all gathered around this iMac, and we like started zooming into the closest thing, pulled up Graphite full screen, and visually just looked, and it was Chef Client. So every 30 minutes, Chef Client ran on our load balancer server. Because it's Ruby, it hit the CPU, and then traffic went down every 30 minutes. It sucked. We figured that out. Chef Client doesn't run on our load balancers anymore, but just visually being able to track it down and see those correlations visually helped us actually figure out what the problem was. So there are obviously limits of visual correlation too. One, it takes a really good eye. You actually have to physically be able to see as a human being what these two things are related, and just be able to know that these ups and downs are actually correlated to each other. This is something that has come up a lot today, but it's hard to see the signal through the noise too. So we have, I don't even know how many metrics in Graphite at this point, 250,000, a lot. It grows every day. And it's really, really hard if you are looking at the CPU time on every box to see what the signal is in that noise, and being able to limit it might help, but it's still really hard. Visual correlation may, but is really hard to correlate to domino style events. So if you had something where, it was really easy because Chef Client happened and then this thing went down, but if it was something where Chef Client ran, dumped 10 gigabytes of log files on the box, the disk filled up, and then something happened, it would be hard to connect those two events together visually because they could be hours, months, weeks apart. Also, we know this about graphs now, but in general, they're good for trends, but not as much for individual events, obviously. You're looking at numbers change, and you want the relative change of those numbers, but it's not really good for hard numbers or little events. So the last one is emotional correlation, and this is my favorite one. I care a lot about people, and I think a lot about people, and that's one of the reasons why I but moved from being just a developer to being the chief nerd in charge, was because I really wanted to deal with people. I love people. I'm an E on the Myers-Briggs scale, if you couldn't tell already. So what I mean by emotional correlation is I just came up with this a couple weeks ago, but I really want to start using it, and maybe as an ops community we can adopt it. I call it Rashomoning. So when you Rashomoning is, how many people have seen the movie Rashomon, first of all? Okay, not that many actually. It's a great movie, Akira Kurosawa. It's one of the classics of Japanese cinema. But basically the story of Rashomon is it's the story of a crime, and the crime has happened already, and basically you're just hearing interviews or basically an adaptation of the story through a bunch of different people's eyes, right? And you're hearing all the different versions of the stories, the movie follows all the different characters, and it's kind of left up to you to decide what actually happened. Kind of like The Usual Suspects. The Usual Suspects had a lot of influence from Akira Kurosawa, obviously. But, so this happens all the time in ops, I think. Rashomoning is something that happens all the time. We all individual, not just silos of data, but we're all experts in something else. And we all know something not only about our own stack, but about stacks in general. So what Rashomoning is each person using their unique knowledge of what happened in the situation to like kind of tell the story together and collectively figure out what happened. And this is really useful, obviously, this is kind of the basis of postmortem and just generally looking back at failures and talking about them. But it's also very, very crucial in live critical events happening. We had a really big failure on Valentine's Day, which we wrote about on our blog. Don't call it the Valentine's Day Massacre, it hurts our feelings. But it was a critical failure on a lot of different points. And it took us all talking to each other, like Jesse was saying, communication is a really key part of this, to really figure out what was going on and what was happening. And if we didn't have that bridge of communication and we didn't actually actively share all our different views of the data, then we would not have been able to see the relationships between them. So obviously, there's some limits of emotional correlation. When you're correlating things through perspectives, it provides a trail, not an answer. Like, no single person, just like in Rashomon, can really like say that this is exactly the series of events that led to this. We each have our different views, and we can present our views, and then hopefully those views mixed together can present a pretty good trail to what was actually going wrong, but it's not the answer. It's not what actually happened. Oswald actually talked about, root cause as being a bad thing, or not a bad thing, but why that's not the ultimate thing. And I think that this emotional correlation is part of that. Like, you can't actually find the root cause. That's maybe not even the point. It's about finding the trail to what was going wrong. It also depends on having a team. Try Rashomoning by yourself. It's really hard. You can do it, but it takes some skill and maybe some voices. You have to have a cadre of voices. You can learn that skill too, but it's okay. So it depends on having a team. I hope a lot of people in here work on an ops team, and I know there are a bunch of collective teams in here. So obviously, you have to trust. Not only does it depend on having a team, but it depends on having a team that you trust to actually provide useful information and share with each other. There also, what we found too, and we kind of have continually trying to iterate on, is the idea of having a judge or a dictator in a moment when you're talking about this kind of all these different perspectives and points of view. You need someone who is ultimately going to say, okay, this is actually the trail that we're going to follow, because you can't have everyone going in different directions. And of course, a limiting factor is just humans in general. Emotions run high during outages or any operational issues, and if everyone doesn't have their emotions in check and are checking their emotional intelligence, which is a term that I like to use a lot, then maybe it's not a good time for them to be telling this story. Cool, so we talked about correlation. Now I'm going to show you how. Actually, no, I don't actually know how to do this at all. But I have some ideas. And actually, we actually haven't implemented really any of these ideas at Paperless Post. It's more just me sending some things out there so that hopefully we can talk about it and maybe make some things happen. So in general, trying to make data more visible is like a really key thing. Not just having data, but making it visible, and there's been obviously a lot of talk about that already today. For us, we created this tool called Hotpot. Hotpot is a conflagration of data, meaning it's like a lot of steamy data, a steamy pile of data all in a single place. So this is what Hotpot looks like. It's not open source yet, but I think I'll be able to open source at least that little beautiful D3 graph that we wrote. But basically what this looks like is that's our Sensu metrics on the right, our Sensu alerts on the right. The circle is the environment. The second ring of the circle is roles, and the second outer ring is nodes, and the last ring is alerts, like individual alerts. So it's cool. I like it because it visually gives us, like, if that whole thing is orange, things are wrong kind of thing, obviously. And also, basically the idea behind it was that we have Sensu data, we have Chef node data and Chef server, we have Graphite data, we have Logstash data. Why can't we visually correlate all those different pieces of data together so that we can see a node and see an individual node and talk about what's going on that node or a collection of nodes by role or by whatever it is. And so that's what Hotpot is. And it's still really early development, and we're not really sure where it's going to go. But we use definitely the graph, and we tend to look at it a lot. The idea is that we have all these disparate sources of data. You just want to align them by some metric, by some collective thing. And that's, for us, that's, aligning them by node and by chef role. Another thing that's come up a bunch today is alerts and alert fatigue. So one of the ideas that I have for hopefully making this better is create relationships for these alerts and notifications. And that doesn't just mean roll-up, but it means actually information embedded in the alerts themselves so you can make split decisions when you get an actual alert. So this is what a Sensu alert looks like now, and this is just some very fancy sketch notes that I have about what I would love to see happen in a Sensu alert. So, we get an alert for disk usage, but maybe there are other alerts on the same box. Those aren't shown in this single alert. Maybe we could just show all the alerts that are happening on this single node. Also, the disk usage is high, but we don't know what the rate of disk usage growth is, and we can't visually see that. Why not just put a graph of disk usage in the alert? There are other, something might have happened, like log rotate failed because CPU was slammed on this box or something. So maybe we can put all the list of all the alerts that are happening at the same time in a single place. And I guess that is sort of roll up, but I mean more just like seeing if a single event caused this stream of alerts. And I think this could be really cool. This is more contentious, but we have not just Pearson's, but other mathematical formulas that could pull out potentially correlated data. Basically, we don't necessarily want to have a machine necessarily tell you that these correlation does not imply causation, that these two pieces of data are exactly related and one is the cause of the other. But we have all this data, we could probably use math to filter out the data so that at least we have a smaller subset of data that we're looking at any given time. Yep, cool. Okay, I'm pretty much done, so that's perfect. So in the world of business metrics, people talk a lot about cohorts, and cohorts are basically related chunks of users, usually that operate on the same set of functions or the same set of goals or funnel. So when we talk about cohorts, really what we're talking about is, can we group related things and then see how those related groups of things, whether they're nodes, processes, or just entire data centers, and how they move together as trends. So Cliff kind of talked about this, but we can definitely, I think, use this same kind of idea to group. I mean, processes obviously aren't people, but we could use the same data and same ideas to maybe group data together. What if we could look at, all the nodes that were bootstrapped on the same day as a cohort? Maybe all those nodes are on the same physical box, and maybe they all have the same clock problem or the same thing. And if we could see that as those nodes are divided by those nodes grouped together, then maybe we could think about how those alerts happen. So into the emotional correlation too, I think this has come up a lot too, but treating personal and institutional knowledge as data is really, really, really important. This doesn't just mean document everything, but that's a really good start. Documenting not just what you're doing, but how you think about all these different apps and tools that we use and how they are related is really, really important for figuring things out. I think just by doing that, you take a lot of the emotion out of emotional correlation. Emotional correlation happens and Rashomoning gets really heated when there's a disagreement between two people about what is actually going on. And so if you made the data available, maybe that wouldn't happen. So if that's just level 2, we're talking about level 2, then what's level 3? Like I said, he ruined my joke, that's Carl Sagan. But level 3 is something amazing and beautiful, and I really, really, really hope we get there. I have no idea what it looks like. It looks like that. And we're all just like, next Monitorama, we're all just like drinking martinis on a beach. That sounds like a good, if we figure that out, then let's all do that. But I think basically that means taking these correlations and these relationships and turning them into actual decisions that machines can make, maybe with a little bit of human help and human interaction, but making that not just automated, but just better, and the interface between them smaller. So we're not there yet, like I said. Let's figure out level 2 first. I want to come back next year or tomorrow and let's talk more about this. So thanks, everybody. That's Yeah, so the doctor himself asked me, he said, so Pearson's goes from a range of -1 to +1. +1 is correlation, -1 is anti-correlation, which means that the numbers are actually not directly related, but inversely related, or just not correlated at all, or the opposite of correlation, basically, that they're not the opposite of correlation, but they're moving in a separate direction. And how would you deal with that? I have no idea is the answer to that question. But I think just generally knowing that what I want to do with Pearson's, or I want to do with the mathematical functions, is apply them to just narrow the data that we're looking at. I don't think we can actually make rational decisions about what we're doing, but if we can narrow the data so that we're only looking at things from above absolute 0.7 or absolute 0.5, then maybe we don't have to look at these other numbers that are just not at all related to the event or alert that we just had. Okay, great, thank you. Great, that would be awesome. Cool, thanks everybody.